Welcome back. In the previous episode, we explained the mechanism behind foam core burning. In this video, we focus on a critical question: what factors actually ignite the hidden internal fire inside flexible PU foam and lead to dangerous self-heating events? We have identified 7 major triggering factors. We strongly recommend reviewing each one carefully against your own production line. 1. Raw material quality. Excessive moisture releases a significant amount of chemical reaction heat. Peroxides and metal ions present in polyether polyols can directly accelerate high-temperature oxidation inside the foam. Low boiling point impurities may cause abnormal volatilization and pressure fluctuations. If the antioxidant system is improperly designed, the foam's thermal stability threshold becomes extremely fragile. 2. Formulation ratios. One red line must be strictly respected. The water content must not exceed 5 parts per 100 parts of polyether polyol. At the same time, the blowing agent system must remain balanced. If physical blowing agents used for auxiliary cooling are insufficient, or if water content is excessive, the exothermic reaction can quickly become uncontrollable. 3. The catalyst balance. In simple terms, amine catalysts mainly drive the blowing reaction, while tin catalysts control gelation. Excessive amine usage causes overly intense foaming, leading to a rapid heat surge. Excessive tin accelerates gelation, prematurely closing the foam structure and trapping heat inside, preventing effective dissipation. 4. Ambient conditions and material temperature. High summer temperatures reduce heat dissipation efficiency. If the initial temperatures of polyether polyol and TDI are too high, the reaction enters a high exotherm phase too early, making it easy to exceed the safety threshold of 170 degrees Celsius. 5. Process-related defects. For example, mismatch speeds between the mixing head and the conveyor belt can create a subsurface flow phenomenon. Unreacted liquid flows beneath already risen foam, causing localized material accumulation. Collapsed zones struggle to form effective gas pathways for heat release, allowing heat to accumulate rapidly in these areas. 6. Mechanical compression. Conveyor belt vibration, overly tight chains, or even a wrinkle in the side film can compress immature foam. This physical deformation damages the cell structure and generates additional heat through internal friction, increasing the risk of self-heating. 7. Storage conditions and operational details. Newly produced foam reaches its peak internal temperature 30 to 60 minutes after leaving the line. During this peak period, stacking is strictly prohibited, and spacing must be at least 100 millimeters. After initial heat dissipation, stacking should not exceed 3 layers. In particular, foam must not be moved, compressed, or stressed before full curing. In addition, factors such as TDI isomer ratios, polyether reactivity, and even atmospheric pressure variations can influence the heat release profile. To summarize, foam core burning is a systemic risk spanning raw materials, formulation design, process control, equipment conditions, and production management. In the next episode, we will move into practical application and explain how formulation adjustments can be used as a reference approach to manage core burning risks. Thank you for watching, and we appreciate your time.